So in the last problem, we identified an answer that came to a single point. That made it a consistent, independent answer because there's only one answer. So any unique solution is a consistent, independent answer. Well, what we're going to look at now is the other types. And so we're going to start with two equations, or two systems of equations. And we're going to start with one first. 2x plus 2y plus 2z equals 12. Minus 3x plus y minus 11z equals minus 6, and 2x plus y plus 4z equals minus 8. And so this is equation 1, 2, and 3. And our first goal is to get this to be an x by itself. The easiest way to do that, since everything is even, is just to take half of equation 1. So that gives me x plus y plus z equals 6. The other equations, of course, remain unchanged because we haven't done anything with them yet. But now we're going to use elimination to get rid of this and this. So we're going to take equation 2 and we're going to add 3 times our new equation 1. And that'll go into row 2. Just like that went into row 1. And then row 3 minus 2 times equation 1 will go into row 3. So I'm going to get 3x plus 3y plus 3z equals 18. And I'm going to get minus 2x minus 2y minus 2z equals minus 12. Now when I add these together, notice that my top equation is still the same, but I get 4y minus 8z equals 12, and minus y plus 2z equals minus 20. Well, my next goal is to get a single y there, and let's just do it this way. Let's just divide everything by 4. We're going to take row 2, and we're going to multiply it by 4th and store it in 2, and I do that because I noticed that 4 goes into all of these. Another alternative would be to swap these rows and change this sign, but this looks like the most direct route to get there. We're going to get y minus 2z equals 6. And our other equation is minus y plus 2z equals minus 20. So now I need to get rid of this y. And if you're paying attention, you might see it already. But here what we're going to do is we're going to take 3 and we're just going to add 2 to it. And so that gives us x plus y plus z equals 6. Y minus 2z equals 6. And y minus y is 0. Minus 2z plus 2z is 0. And 6 minus 20 is minus 14. Notice that 0 can't equal minus 14. This is a contradiction. That equation can never be made true, and since it's part of our set, the whole thing is inconsistent, and you get no solution. So if in your steps of solving the problem, you get to the point of a 0 equals a number, then you're done. You can't go any farther. It's simply an inconsistent system. And if it's inconsistent, then it's neither dependent nor independent, so we don't need to worry about it anymore. Well, I also wanted to show a different type of equation. What if we had x plus y plus z equals 5, minus 4x minus y minus 8z equals minus 29, and 2x plus 5y minus 2z equals 1. So 1, 2, 3. 1's already in good shape, so we're just going to take 2 plus 4 times 1 and store that in 2. And we're going to take 3 minus 2 times 1 and store that in 3. So that's going to give me 4x plus 4y plus 4z equals 20, and minus 2x minus 2y minus 2z equals minus 10. So when we add these together, we still end up with our x plus y plus z equals 5, 0x, 3y, minus 4z equals minus 9, and 3y minus 4z equals minus 9. If you look very closely at 2 and 3, you'll recognize that these are the same. So no matter what I do, even if I were to put a 1 here, when I go to this step, let's just take 2 minus 3, for instance, so let's go minus 3y plus 4z equals 9. Notice our last equation here this time is going to be x plus y plus z equals 5. 3y minus 4z equals minus 9, and 0 equals 0. Whenever I see this 0 equals 0, or I recognize that I have the same equation twice, this makes this a dependent system. And all I need to do now is to get my parametric answer. So I'm going to take this equation 2, and I'm going to solve for y. And so in this case, we're going to get 3y equals 4z minus 9, so y equals 4z minus 9 all over 3. That's my y. And then I go back to my first equation, and I plug this in for the y value. So I'm going to get x plus 4z minus 9 over 3 plus z equals 5. Well, that's x. Let's just multiply everything by 3 real quick. We'll deal with it again later. And we're going to get 3x plus 7z minus 9 equals 15. So 3x equals minus 7z, not x, that should be a z. And when we add, that's a plus 24. When we divide by 3, we get x is minus 7z plus 24 all over 3. And this becomes our answer. So our answer is this parametric answer where the x depends on whatever z is. The y depends on whatever z is, and the z is just z. So I could actually write this without the x or the y. And here's my parametric answer. Here's my x, my y, and my z. And I can get points by picking a z, and that will give me the dependent y and the dependent x. So whenever we end up with a 0 equals 0, we have a dependent system, and we solve for it parametrically.